Hi, Bitcoin class. This is my attempt to explain a few of the cryptographic subtleties about Bitcoin that has important consequences. So it's a clever thing. So maybe the first thing I want to point out is so wallets do not store Bitcoins. That's a whiteout spot. Do not store coins. It's kind of weird, right? Because you think of wallet, like you put your money in a wallet, but instead they store the private keys, which then that lets you spend Bitcoins. So the ledger, which is public, it's sort of interesting. Essentially, everybody throws all of their money in a pile, big public pile. All right, so there's I guess, and that's the blockchain. So the blockchain, there's ledger entries that respectively imply certain amounts of Bitcoin. And the ledger is public, right? Everybody has access to it, you copy it all down. So really, what's in your private key is the right to add into the transactions a new transaction, which lets you combine some subset of these, right? And then transfer that ownership to somebody else in the outputs. So inputs to outputs, right? So the inputs must be signed, right? That's one of those rules. The inputs must be signed. And so unless there's something broken about the cryptography of the system, or you have somehow leaked your private key, only people with the private key can do the signing. So if your wallet is keeping track of the private key, then only you can sign a transaction that transfers the ownership of your Bitcoin to some other address in the ledger system. So so now let's talk about those addresses, maybe a bit in review, but some new features, or perhaps of how that works. So then, just kind of to reiterate this thing, it's sort of an odd thing I think to get in your head. So Bitcoin wallets don't store coins. Coins are on a ledger. What they do store is the right to transfer coins between some place and some new address. So how does the addressing scheme work? All right. So basically, it's a three-step process. So there is what's called a private key, and that is 256 random bits. All right, and then that key is used to generate a signature. So we'll call this, I guess we'll call it SEC for secret key. All right, and so the action is to take this secret key, and in this sense, there's a sense of multiply, and this is what the book uses for the notation. So the sense of multiply, where you take the secret key and multiply what's called the generator, and everybody knows what the generator is, it's a public knowledge thing. So, and this then becomes an intermediate key, all right? And you need that in order to sign transactions, all right? Then that is transformed further with actually two hashes. One's called WriteMD, and then the SHA hash. Actually, this is a 160 bit, and this is a 256 bit one. And so you take this value as the input, and you compute the SHA, and take that, take the right MD160, and then this is the address. So for corresponding private key, you do really three transformations before you get to a key address on the other side. Now the key address is 160-bit address. It's encoded in various ways, and so you can use, I guess, a base 58 encoding. So we've talked about different kinds of number encodings. Base 10 is the way normal day-to-day transactions of numbers are talked about. But you can use other bases. Instead of 10 symbols, if you have 2, you can write it out in powers of 2 instead. So base 10 is written in powers of 10, right? So 732 is 7 times 10 squared plus 3 times 10 to the first power plus 2 times 10 to the 0, right? 10 times 10 is 100. 10 times just 1 time is 10. 10 multiplied 0 times gives you 1. You do this arithmetic, you get that. So, so this is the number of symbols available in the system, right? And then you just choose which one you write down to give you the place value in here. And so that's base 10, and base 2, the power 10 is replaced by 2. And base 58, base 58, it's essentially the alphabet plus letters and digits, and then minus a few super easy to mistake things like lowercase l and capital letter O are removed so that you don't have confusion between what's written if you wrote it down and accidentally flipping those sorts of digits around. So base 58 encoding uses a large number of symbols that are just commonly available, essentially via what's called the ASCII table, just common letters that are transferred. And the bigger the base, sort of the shorter, the fewer number of symbols it takes to write down a number. So this sort of shrinks the number of symbols you need to write down in order to write down the address. So base 58 encoding is normally what you see for those addresses. All right. So, why is this cool? So if you have some in the ledger, right? If you have some ledger that says, there's 4 Bitcoins, and then goes to, we'll call this capital A, goes to some address, right, is owned by this address. And this is one of many transactions in one block, and then the blocks continue over time as they do. Then anyone that's aware that you own, that you control that address, would say that that's your Bitcoin. Now, there's not necessarily any reason that is true, because you can generate them privately, and so there's no reason that the world would know really who in fact owns the private key or has access to the private key in order to do a signing to change anything about the fact that this address is owned, that these 4 Bitcoins are owned by this address. So there's no association to a person necessarily, just an association to an address. So so a few interesting things. So the private key really never needs to be used in the blockchain. What it needs to be used is essentially this piece. I guess along with that piece. So what needs to be used is to create a new transaction where it takes some address. So 4 Bitcoins, well, actually use all of the Bitcoins from one address. So you take some address and move it to some new address. Well, the only way you can add that transaction in the blockchain is if you sign via your secret key. You need the secret key in order to properly create such a signature. So, so you can't spend it without access to the public key and then the ability to sign a transaction. All right. And Dr. Reichenbach pointed out that there are hardware wallets where the hardware wallet keeps track of the private key, and all it does, or all you're allowed to do with it, is to use the private key in order to create these signatures. It never actually exposes the private key to anybody it only has enough resources or enough mechanism in there to sign using that private key. And that way, there's the signature, I guess the other thing to know is the signature itself doesn't reveal anything about the private key. So the signature doesn't help you somehow steal somebody's private key by looking at a signature. It doesn't allow you to duplicate it, which is an interesting thing about digital signatures. So digital signatures, you see a signature or something, does not allow you to create a forgery. So these signatures, these signings can be done by a machine. I mean, it's a complicated enough step that you cannot do it by hand. So you need a machine to help you do this. But you can report a public address and people can spend money and send it to you, for example, so long as you don't lose the key. And the send to you really is just to say that certain Bitcoins are sent to some address that's on the ledger. And you have no rights to refuse that a recipient, right? Because there's no signing on the other side to receive a Bitcoin. All it has to be is that address is sent somewhere. So that address being sent somewhere means it could be anybody's address. How that was formed is a matter of, it's sort of off the chain. Somebody has to decide what address to send to. Okay. So this mechanism allows for the idea of cold storage. Right. So, and it's a funny thing, right? So the Bitcoins are themselves really just records in a ledger. And if that feels funny to you, maybe you should, maybe instead of thinking the analogy of Bitcoins as gold, think of it as Bitcoins is value of your checking account, right? So the amount of money that's in your checking account is not represented by some stack of bills somewhere, right? The value of money in your checking account is in fact an entry in a ledger. It's electronic, it's a database, but it's just an entry in a ledger and it's just a number. And so your ability to maybe add or withdraw from that, I think actually follows a pretty close analogy to that. Most of the time people are not, actually I think in the checking account, you need a certain amount of agreement on both sides. So you're not allowed to just put money into somebody's checking account typically without the recipient authorizing it as well. So that actually is not true in Bitcoin. In Bitcoin, anybody can drop money into your checking account. The authorization is the output side. So if you want to take money out of your checking account, you're supposed to be verified as the owner of the account. And the Bitcoin analogy is that you have the private key so that you can do the signature to sign off on some transaction like this. So the idea of cold storage is that you can take this private key and put it somewhere like on paper, right? So it is just 256 random bits. So there's lots of ways to create that idea. I don't know if there's convenient ways. So you can certainly use software to help you do that. You can also just say roll a bunch of coins or toss a bunch of coins and just record all of them. That'd be a lot of coin tosses. You can get dice that have 16 sides, if you remember hexadecimal. So you can roll a 16-sided die, and that way you get basically 4 at a time, which reduces the number of times you have to roll. You get a group of them, you can start creating 4 at a time, and a few rolls will give you this many bits. What's nice about those sorts of steps is you're not relying on anything else for the point of view of randomness, and that's a nice thing. So private key you can create, and then, I mean, truly you do need hardware to be able to do the signatures and to create addresses. There's enough details in there. It's just too much work to do otherwise. But the private key doesn't have to be anywhere that other people can access it. And that's the idea of cold storage, is to create a private key. You can, so for example, create the private key, right? Record it carefully, maybe in triplicate or something like that, and do not want to lose a private key. And then you have to trust some machine, and the machine can be completely isolated from the network because it has to do just these calculations. It has nothing to do with the blockchain. It's all well-known algorithms. that are just part of a specification that don't involve needing to connect to the internet or anything like that. These algorithms are well established. So you could take a private key, enter it into some trusted system, right? Trusted system. And then in there, you do this, you go from the secret key to the derived key, the address. So, and then print out the address, right? So you have this on paper, and now you have this on paper. So this address is really all you need. So if you're willing to have that address in ways that's convenient, and there's things like QR codes and that sort of stuff. And really, once you get to here, this is sort of easy to. You can share this. I suppose the one thing to be a little cautious about when I say share this, if you sent an email with this address in it, you are in fact making an association between this address and you as a person, right? So if you were trying to be anonymous about being the recipient of Bitcoin, by publishing an address that is associated with your name somehow or through some chain of reasoning belongs to you, then in the end, you break the idea of the anonymity, and really it's a pseudo-anonymous thing because in fact the whole chain is public. But essentially, if you want to make sure that people don't know who belongs to this address, you need to think about how it's shared. So the Bitcoin network, choosing where it's dropped in and which nodes, you can create virtual private networks to drop in from different locations. Or you can create an address that's available for receiving Bitcoins. And then really offline as a piece of paper, as something you stick in your, like a safety deposit box at a bank, or make multiple duplicates of, you can use that mechanism to keep track of private key. And as far as other people adding information to, adding value, adding Bitcoins to that address, it is okay to have an output go to an address without a signature. So this part is not needed to receive Bitcoin. So long as the address is published, people can send money to it. And nobody has to really know who that address belongs to, although in some cases, so other requirements might show up. So for example, we mentioned Coinbase is a trading account in the United States. Well, fiduciary laws in the United States require that they know who belongs to that trade. So who belongs to that organization for the purposes of making trades. And so they do establish an ownership idea, and that's a requirement by US law, but it's not a requirement by the technicalities of Bitcoin. It's just a matter that as an exchange in the United States, they're required to report what US dollar amounts are used in that exchange, and so they need to collect that kind of information. Okay. So let me just talk about a couple of other ways to generate private keys that seem interesting. So, well, first, maybe one that's a little dangerous. It's sort of good and bad. The idea of a brain wallet was mentioned. And so to create a private key, you want to create this much entropy, which is the same as throwing 256 random coins. Well, there's a lot of ways to do that. And if you think about like the SHA-256, for example, will generate 256 bits of mixed entropy, essentially, out of any long string of stuff. And so you could choose words. Just append them all together like this. And so if you have a pretty good list of words, so say you have 1,000 words, and then you choose at random, this is important, choose at random 1 out of 1,000 words. Well, this is very close to 10 bits of entry. If you want to be exact, it's 1,024. If you had 1,024 words to pick from, and you completely chose at random one of the 1,024 words, that gives you exactly 10 bits of entropy. So for every random word, and then repeat that, and with the possibility of just choosing the same word again, you might end up with the same word every time. But every time you do that, you increase the randomness by 10 bits. So if you chose out of 1,024 words, let's see here, 10 bits. So basically, if you did it 26 times, so you had 26 words chosen at random from the same list, just repeated on that whole list, that would give you 256 bits of entropy. So that's considered overkill in the sense that if somebody else is trying to hunt down your private key, 256 bits is so beyond the pale of trying to guess from a computational point of view about which one it could be, that you really don't need that much entropy. Usually a high bar in cryptographic sense is 128 bits of entropy. Is considered like military hard, like the idea that somebody else is going to have enough computational resources to break 128 bits of entropy is just unreasonable. It's unlikely. I'll say even impossible right now. And so if they're trying to break 128 bits of entropy using the schemes that we just did, where you take the bits of entropy, you do the public key derivation step, and then the 2 hashes, and then see if some address shows up and use that to sort of dictionary attack an address. Actually, 128 bits of entropy is totally enough. And so if you think about this, 10 bits, that means really 13 words should be enough. And it should make sense. If 26 words is enough for 256, then 13 should be good for half. So you could try to come up with 13 words, and then the thinking is, again, if you are willing to spend the time and effort, you should be able to remember 13 words. And the nice thing about 13 words also is, you can publish the 1,000. Like, there's nothing that needs to be secret about this word list. So you can print out, and stick it on your wall, the 1,024 words that you chose from, and then write down in secret what these 13 words are. And the idea is that even if the attacker knew this list, by the time you've chosen 13 repeated at random words out of there, there's so much entropy involved that there's no way that they will be able to compute that or find them. So the great danger in this is 13 words is a daunting amount of entropy to try to memorize, and people try to, I'll do something simpler, and they'll choose 8 words or something like that. Since there are Bitcoins at stake, people know what the schemes are and do these sorts of attacks on addresses. And so if you choose what you think of as, in normal settings, like a good password sort of style of words for a brain wallet, you might easily lose your Bitcoins. So if you don't really want to, if you don't hit this very high bar of a brain wallet, then just realize that the protocols are well known, and if you use a brain wallet and kind of cheat it and give it a set of words that really were not chosen at random, that's another big mistake. You look at the 1,024 words and say, okay, I'll just kind of do it by hand at random instead of rolling dice to find these. They have to be truly random to get this amount of entropy. You can just like go through and try to pick things so that like they start to make sense, or in some sort of chain of reasoning, the entropy drops way down. And those sorts of word searches are much easier to do. So for this brain wallet idea to actually be secure, most of the systems really create the word list and the words for you, and you just get the one that it gives you. You don't change it. That represents truly 256, or in that case about 260 bits of entropy if you went all the way to 26 words, 13 words, 128 bits. But it gives you a strong bar for the amount of entropy that's included in the address. So let me finish that thought a little bit. So you take whatever the brain wallet produces as a word list, take it through a SHA-256 hash, and that would produce 256 bits, because that's what a SHA hash does. And then that's considered the private key for the rest of that chain of command that happened before. So once you've done this step, this gives you a way to derive that private key. So so on to the next. So there's ways to do things like hierarchical keys as well. So if you trust that this is a very secure mechanism, then perhaps you can see that there could be other ways to generate like related keys in this whole sort of setup. So a simple version of this, and this is not quite how it works out, but if you took this brain wallet and then at the end of it said maybe appended number 1 to the end of it. So that would be a way to derive a key that that would be a random would be a private key that then could go be used in the Bitcoin ledger, right? But then if you just used exactly the same sequence, but then added number 2 and then took the SHA-56 hash of that, right? From the point of view of the system, because SHA-256 is what it does what it does, it will look like essentially a whole new random set of 256 bits. So this would be, secret key 1, and then if you just appended a #2 on the next one, you could generate secret key 2, which would look completely independent of each other. They wouldn't look like they had anything to do with each other. But in the background, there's some sort of simple way of deriving these keys. So the book talks about this idea of hierarchical keys, where keys can be used that can be derived from each other. And essentially it comes from this sort of a hash sort of style of producing these keys. So, so there are hierarchical keys. What's interesting about them is they allow for a certain amount of accountability for what set of keys are allowed or accessed. And so kind of getting towards that idea of accounting as software. I know accounting as software is, of course, accounting software. There's all the software written for QuickBooks and all that stuff to manage accounts. But now, what is the problem with software? Software plays by the rules unless somebody who wrote the rules wrong in the code or some accountant, kind of cooks the books. So it is possible to create ledgers in the Bitcoin blockchain that are auditable in public, that you can prove that what is done is valid and sort of known publicly. So the hierarchical keys kind of give you access to that without speaking too much of the details. Okay, so that one, let's see if I have, we'll call that pretty good. So the brain wallets really involve, just to summarize, so there's this idea of a secret key, then going to a public key that can be used for signing transactions, which is secret times generator, and then a hash, which is really a combine of several hashes of that same secret times generator. That's the address. So secret times generator is the public key, and then the secret is the private key. So that chain of command, and this is 256 bits. This. The address out here comes out to be 160 bits. And so with that set of ideas, and again, with the idea that the wallets don't contain the Bitcoins, the wallet contains the private keys, which allow you to sign off on transactions. So now, if you can derive a bunch of wallet addresses, these addresses, private addresses, using some scheme like this, then it's actually possible to create many, many addresses based off of a relatively small amount of information. And so that's another nice thing about these sort of derived keys or hierarchical keys, that really there's not very much information at their core, but there's enough information, 128 bits or better, of entropy at their core so that nobody else could reconstruct it. And then from that, from those private keys, you could create a whole category of addresses that you know why they're related to each other, but nobody else needs to know why they're related to each other. Okay, I'm going to call that good for this lecture.